All right, let's dive into something pretty cool today. We're talking PokéChamp.
PokéChamp.
Yeah, have you heard about this?
Oh, yeah. I've seen it around, yeah.
This is a new AI developed by researchers at Princeton. And it's making waves in the world of competitive Pokemon.
That's right.
We're not just talking about an AI that can play the game. This thing is reaching expert-level ranks, beating top human players on Pokemon Showdown and leaving other AI bots in the dust.
It's really remarkable.
Yeah, and that includes AI systems powered by large language models. So this is kind of a step change in what we're seeing in AI for gaming.
Absolutely.
So we're going to unpack how they pulled this off. We're going to be doing a deep dive into the paper PokéChamp, an expert-level Minimax language agent.
Right. What's interesting about this paper is it takes this really fundamental game theory algorithm called Minimax tree search and enhances it by using the knowledge that's within large language models to play this complex game of Pokemon Battles.
And it's not just the paper itself we're looking at, right?
Yeah.
We've got a whole bunch of stuff to base this deep dive on. We've got the details of PokéChamp's architecture, how it actually makes decisions.
Yeah.
You know, how is this AI structured? We're also looking at the performance evaluations, how it actually performs against other bots and human players on Pokemon Showdown. And they've also put together this massive data set of over 3 million Pokemon battles.
Wow.
Yeah.
That's a lot of battles.
And they've created these really interesting benchmarks and puzzles specifically to evaluate PokéChamp. So really trying to put it through its paces.
That's great.
So what we're trying to figure out in this deep dive is, how can PokéChamp, without any specific training on Pokemon, leverage LLMs to reach this expert level in this really complex game?
It's a partially observable game as well. You don't see everything that your opponent has. You have to deduce that as you play. So what does this tell us? How does it do this? And what can we learn from this about combining LLMs with classic game theory algorithms for just general AI research?
Yeah. So if you're looking for that kind of 1-minute summary, before we get into the real nitty-gritty, here's what we're looking at. PokéChamp, this new AI for Pokemon Battles, performs at the level of top human players. It uses LLMs to do that. And what it does is it takes this classic Minimax search algorithm and uses LLMs to enhance it. So it uses LLMs to kind of guide the search, and it does that by using LLMs for things like figuring out which actions it should even be considering in the first place.
Okay.
And then also anticipating the opponent's moves and evaluating how good the board state is. How good is the current state of the battle? So it uses LLMs to do all of that stuff. And remarkably, it does all of that without any training on Pokemon specifically.
Wow.
Just using the LLM's existing knowledge.
That's really fascinating.
It is, right. And so they found that it beats other LLM-based bots. It beats traditional rule-based bots and reaches this projected ELO of between 1,300 and 1,500.
Wow.
And on top of all that, they've created this huge data set of 3 million Pokemon battles for everyone to play with. That's the overview. Now let's really get into the meat of it.
Yeah. So let's start by just understanding why Pokemon battles are such a difficult challenge for AI. I mean, on the surface, you might think, oh, it's a fairly straightforward game.
Right.
But underneath, there's this huge amount of complexity.
Oh, absolutely, yeah.
And it's really, really challenging. There are more than 1,000 unique Pokemon.
Yeah.
And each of them have their own different abilities, different moves, different types, and their stats that affect how they play.
Oh, yeah. It gets crazy, right?
Oh, yeah. The researchers actually estimate the number of possible game states you could be in on just the first turn.
Right.
It's more than 10 to the power of 354.
Wow. It's basically like a combinatorial explosion. There are just so many different possibilities.
Yeah, it's almost infinite. And it's very different to games like Go or chess, where you can actually see the full board and the full state.
Right. You have perfect information.
Yes, you have perfect information. In Pokemon, you only see your own team, and you can only see the opponent's active Pokemon. Right, yeah.
You don't see the rest of their team. So that information is revealed to you as the battle unfolds.
Gradually, yeah.
Yeah. So you're constantly making decisions with incomplete information.
Absolutely, yeah. And this is a really important point, right? Because a lot of classic game-playing AI algorithms really rely on having perfect information about the game state.
Absolutely.
And they don't really deal well with this kind of uncertainty.
Yes.
And also, it's not just one move and then it's over, right?
Yeah.
These are long battles. A single battle can range from a few turns to over 100.
Yeah, that's right.
So you need this long-term strategic thinking to be successful. So given all of this, why even think about using LLMs? Why are they a good fit for this problem?
Yeah, well, LLMs have shown this really incredible ability to learn patterns and generalize knowledge across a whole range of different domains.
Yeah.
And they're trained on this massive amount of text data. And it's very likely that a lot of this data includes stuff about Pokemon strategies and competitive play. I'm sure there's plenty of that in the training data.
Oh, yeah, for sure. So they come with this kind of prior knowledge of the game, and that means that they could potentially understand the strategic landscape of Pokemon without even being specifically trained to play the game.
Yeah. So they're kind of like these universal knowledge bases that we can tap into, right?
Yeah.
But it's not quite that simple, though.
No, it's not, because previous attempts to just, give LLMs a text-based description of how to play a game and then have them play have generally not worked very well.
Right.
They seem to understand the rules and the concepts, but they struggle with things like planning and, doing those actions that are actually required to play the game, and also the long-term strategic thinking that's necessary to be really good at the game.
Right. It seems that just giving them text about the rules isn't enough. They really need something more to actually play effectively.
Yeah.
So what PokéChamp does differently is it doesn't just try to get an LLM to read about Pokemon and then play. Yeah. Right? It's much more integrated than that. It leverages this knowledge that the LLM has, but within a more traditional game-playing framework.
Right.
And that's where this Minimax algorithm comes in. So let's actually dive into the architecture of PokéChamp. How does this thing actually work?
All right, so the key idea is that PokéChamp takes this Minimax tree search algorithm and it enhances 3 critical components of this algorithm using large language models.
Okay, so it's like it takes this classical algorithm and injects this LLM knowledge into specific parts of it.
Exactly.
Okay, so let's break down these 3 enhancements. What's the first one?
Okay, so the first one is player action sampling.
Player action sampling. What does that even mean in the context of Pokemon?
So think about what a player can do on any given turn. They can select one of their Pokemon's 4 moves, they can switch to another Pokemon, or maybe use a special mechanic like Terastallization or Dynamax, depending on the game generation.
All right, lots of choices.
Yeah. And ideally, a Minimax algorithm would explore every single one of these actions and every possible response the opponent could take. And you'd build this huge tree of all the possibilities.
You'd search all the way to the end of the game, right?
Yeah, but as we talked about, Pokemon's just so huge that becomes impossible to do.
Way too complex.
Yeah.
So many possibilities.
Yeah. So what the LLM does is it basically acts as this intelligent filter.
Okay. So it's going to cut down that search space.
Exactly. It cuts down the number of things you need to consider. So PokéChamp gives the LLM this rich context about the current state of the game. This includes the AI's overall plan, how it wants to play the game. It also includes the observable game state, so things like which Pokemon are currently active, what the current status conditions are, what items are in play. And it also includes the history of the moves played so far in the game, and even like a quick approximation of how different actions might play out in the immediate future.
So it's giving the LLM basically all the information it has.
Yeah.
Everything.
Yeah, a really big picture.
And then what does the LLM do with that?
So then the LLM takes all of this information and it just samples a small set of actions that it thinks are going to be the most likely to be good strategically.
Okay, so it's not generating actions. It's choosing from the existing ones.
Exactly. It's choosing and it's saying, hey, these are the ones that are worth looking at in detail.
Okay.
And that means that the Minimax algorithm can just focus on these actions.
Right. And it makes the whole process much more efficient.
Yeah, exactly.
So it's like having an expert player, like a really good human player, come in and be like, hey, these are the 3 moves I would actually consider in this situation.
Right.
So we don't have to search millions of possibilities. We just look at those 3.
Exactly.
But the paper mentions that it doesn't exclusively use the LLM. It also uses a couple of other techniques as well, right?
That's right. So just to make sure it doesn't miss anything, PokéChamp also considers the top move suggested by just like a really simple 1-step look ahead. This is basically like what move does the most damage immediately.
It's just the greedy move.
Yeah, exactly. And it also considers the best switch suggested by another AI called the Abyssal bot.
Okay, so this Abyssal bot, is that another LLM-based bot?
No, so the Abyssal bot is this really good rule-based AI that's known for making good switching decisions.
Okay, so we've got these 3 components. We've got the LLM suggestions, we've got this simple 1-step look ahead, and we've got this Abyssal bot suggestion for switching.
Yeah.
And then what happened?
Well, then all of these are fed into the Minimax search.
Okay, so it's combining these multiple sources to make sure that it's covering all the bases. It's not getting tunnel vision.
Exactly.
Okay, so that's player action sampling, right?
Yes.
So that's one of the 3 enhancements. What's the next one?
Okay, so the next one is opponent modeling.
Opponent modeling, okay. And this seems really crucial given that we're talking about this partially observable game where you don't see all of your opponent's information.
Right.
You don't know what their team is or exactly what they can do. Yeah. So you have to try to figure out, what they might do.
Predict it.
Yeah. So PokéChamp uses the LLM to actually forecast the opponent's most likely actions. And the prompt that it gives to the LLM for this is really similar to the one it uses for its own action sampling.
Okay.
But it's framed from the perspective of the opponent. So it's saying, hey, if I was this opponent, what would I do?
Given all the information we have available.
Yeah.
Okay. And I know that they use the big data set that they created of 3 million Pokemon battles.
Yes.
So how does that data fit into the opponent modeling?
So they use that data to deal with the uncertainty surrounding the opponent's Pokemon stats.
Okay. Because you don't know their exact stats, you don't know their attack or defense values.
Yeah, exactly.
So how do they figure that out?
So PokéChamp uses this data to estimate what the probability distributions of different stat builds are for the opponent's Pokemon.
Okay.
And it does that based on usage patterns at different skill levels.
Okay, so they're using the data to see what good players tend to do in this situation.
Yeah,
right?
exactly.
If this Pokemon is used by good players, what are their stats likely to be?
Yeah.
Okay.
And then it can combine the LLM's ability to predict strategic actions with the statistical probabilities of the opponent's stats to build a better model of what the opponent might be capable of.
Right, yeah. So it's combining this LLM intuition with real data about how people play the game.
Yeah.
That's pretty cool.
Yeah.
So we've talked about player action sampling. We've talked about opponent modeling. What's the third and final area where LLMs are used?
So the third area is value function estimation.
Value function estimation. Okay, this sounds a bit more abstract.
Hell.
What exactly is this, and what does the LLM do here?
So ideally, the Minimax algorithm would search all the way to the end of the game, right?
Until there's a winner.
Yeah. But of course, we can't do that because it's just too computationally expensive.
Right.
So in practice, you have to limit how far you search. You have to say, okay, we're only going to look this many moves ahead.
Right.
And then when you reach that limit, because the game hasn't finished yet, you need some way to estimate, okay, how good is this position?
Right. You need to evaluate that state of the board even though you haven't searched all the way to the end of the game.
Yeah. So how favorable is this situation, even though we don't know for sure who's going to win yet?
Right, because you haven't actually finished playing it out.
Yeah. And that's what the value function does.
Okay, so it gives us like a score of how good that position is, even though we don't know the final outcome.
Yeah, exactly.
Okay, so how does PokéChamp use an LLM to do that?
So PokéChamp prompts the LLM to evaluate the state of the game at the depth limit of its search.
Okay.
And this prompt includes a whole bunch of different factors that might indicate a strong or weak position.
Okay, like what?
So positive factors might include things like how effective are your Pokemon's moves against the opponent's current team?
Makes sense.
You know, how many Pokemon do you have remaining versus the opponent? And then also, you know, is there a good chance you're going to win the game overall?
Okay, so these are all things that would indicate you're in a good spot.
Yeah. And then on the negative side, you might have things like, have you had to switch excessively? Are the opponent's moves super effective against your team? Do you have a speed disadvantage?
Okay.
You know, or does the opponent have more Pokemon or really strong Pokemon remaining?
Okay, yeah. So these are all the things that we would think about as good human players as well, right?
Yeah,
We would intuitively consider these things when evaluating a position.
absolutely. And then what the LLM does is it takes all of this information and spits out a numerical score that basically represents the value of that game state.
Okay, cool.
Yeah.
So it's giving us this numerical score that we can then use in our Minimax search to figure out the best move.
Exactly.
Okay. And the paper highlights that the LLM is functioning as a black box. So what do they mean by that?
So they mean that the LLM hasn't been fine-tuned or trained on any Pokemon-specific data.
Okay.
It's just using this existing knowledge that it has from its massive pre-training.
Okay, so it's just using its general knowledge.
Yeah.
It hasn't been specialized for Pokemon.
Yeah, and this is really important because it means that this method could potentially be applied to lots of other games and other domains as well.
Right. And it makes the whole thing a lot easier because you don't have to go through this process of collecting a huge amount of data and training the model on that data.
Right.
You're just leveraging the knowledge that's already there.
Exactly.
Okay. Now, one thing I was curious about was, how does PokéChamp deal with the randomness in Pokemon? So, things like moves have a chance to miss. There are critical hits, these random elements. And the paper mentions this term, approximate game transition.
Okay, yeah. So because PokéChamp doesn't know everything about the opponent's team, it has to make an inference about that hidden information, right?
Right. It's using the statistics from Pokemon Showdown. It's using its LLM predictions.
Yeah, exactly. And then once it's got, its best guess about what the game state is, it uses this local game simulator, which is basically like a simplified version of the actual game, to simulate all the possible future moves that it's considering.
Okay.
And to make the simulations manageable, it simplifies the randomness by calculating what the expected outcome is, rather than playing out every possible random event.
So, for example, if a move has a 90% chance of hitting, it's not going to simulate 100 battles where sometimes it hits and sometimes it misses.
Right.
It's just going to say, okay, on average, we expect this move to do this much damage.
Exactly.
Okay, that makes sense. And I noticed they even put the entire formula for damage calculation in Pokemon in the paper.
Yes. It's a very intricate formula.
Oh, yeah. It's super complex. It takes into account the Pokemon's level, their stats, the base power of the move, all these type matchups, the weather, all this stuff.
Yeah.
And it seems like that damage calculation is really important for that one-step look-ahead heuristic that they're using.
Absolutely. That damage formula is really the core rule that governs what happens when you attack in Pokemon. So the one-step look-ahead uses that formula to work out, okay, if I use this move, how much damage am I actually going to do?
Okay, so that gives it that immediate tactical awareness?
Yeah.
Okay, cool. So we've talked about how PokéChamp is put together. Now let's look at how well it actually performs. So they start by analyzing this huge data set that they put together. 3 million battles. That's a lot of battles.
It is, yes. It's a really valuable resource for understanding how competitive Pokemon work.
Yeah, absolutely. And they highlight that it includes more than 500,000 matches between high ELO players. So these are like the best of the best.
Yeah.
And by analyzing all this data, they were able to figure out, what are the team compositions that people are using? What are the moves they're using? The common strategies? And I noticed they've got this interesting figure in the paper, figure 5, where they actually show the distribution of skill levels across different game formats.
Yeah, it's really interesting.
They use the ELO rating system, which is this measure of skill. And you can actually see how that's distributed across different formats. And they also looked at the correlation between how long the battles are and the ELO rating of the players.
Yeah.
And it seems like the better the players, the longer the battles tend to be.
Yeah.
Because they're doing all the strategic maneuvering.
Absolutely.
Okay, that's cool. And then they also did some experiments trying to predict what human players are going to do.
Yeah, so they wanted to see how accurately they could predict what move a human player would make given a particular game state.
Okay.
And this ties back into the whole opponent modeling thing that we were talking about before.
Right, yeah, because if you can predict what your opponent's going to do, you're going to have a massive advantage.
Yeah, for sure. And this was actually really hard to do because, remember, Pokemon is partially observable.
Right, you don't have all the information.
Yeah. And even the replay data that they were using, that's normally from the perspective of a spectator.
Right, it's like watching the game, not playing it.
Yeah. So they actually had to process that data to try and figure out what each individual player would have known at the time they made their move.
Wow. Okay, so they're reconstructing the information state of each player.
Yeah.
That's pretty intense.
Yeah.
So how well did they do? How accurately could they predict human moves?
Well, Table 1 in the paper shows the results. And unsurprisingly, predicting the opponent's moves was much harder than predicting the player's own moves.
Okay.
But in both cases, the LLM predictions were much better than random guessing.
Okay, that's good. It means that the LLM is actually picking up on something.
Yeah. And they also found that if you look at the top few most likely actions that the LLM predicts, the accuracy gets even better.
Right, so even if it doesn't pinpoint the exact move, it's usually within the set of moves that are actually plausible. Okay, that makes sense. So they analyzed this big data set. They've done these experiments trying to predict human players' actions, and then they moved on to evaluating PokéChamp in these controlled scenarios that they call small game puzzles.
Yeah. So these were designed to really isolate specific parts of PokéChamp's decision-making process and see how well it does.
Okay.
And they started with 1,000 different one-on-one Pokemon battles.
Okay, so very simplified, it's just one Pokemon versus one Pokemon.
Yeah. And they set it up so that there's a clear winning condition. You know, there's some sequence of moves that will lead to a victory. And they want to see if PokéChamp can find that.
Okay.
And they actually compare PokéChamp's performance to another LLM-based bot called PokéChamp.
Okay. How do they compare?
Well, PokéChamp got a much higher win rate. It won 86% of the time compared to Pokemon's 76%.
Okay, so it's a significant difference.
Yeah. And the researchers think this is because PokéChamp is using this one-step look-ahead heuristic really effectively in these situations. Because when you don't have to worry about switching Pokemon, that one-step look-ahead becomes really powerful.
Right. It just becomes about maximizing immediate damage.
Yeah.
Okay, that's cool. And they didn't just do these one-on-one battles. They also created puzzles to test these more complex game mechanics like terrestrialization and Dynamax.
Yeah.
These are more recent additions to Pokemon, and they really shake things up.
Yeah. So terrestrialization lets you change your Pokemon's type once per battle. And Dynamax lets you temporarily make your Pokemon much bigger and stronger.
So these are big strategic decisions that you have to make.
Yeah.
And they wanted to see if PokéChamp could actually understand these mechanics and use them strategically.
Yeah, and it turns out it can. Figure 6 in the paper shows some really nice examples of this. You can see how PokéChamp used terrestrialization to completely turn around a bad type matchup.
Okay.
And they also show how it used Dynamax to get multiple knockouts in a row.
Okay, that's really impressive. So it's not just understanding the basic rules, it's actually understanding these higher level mechanics.
Yeah, absolutely.
Okay, so it does well in these controlled environments.
Yeah.
But of course, the real test is how does it do in a real game against other bots, against humans?
Yeah. So they tested it on Pokemon Showdown, which is this online platform where people play competitive Pokemon.
Okay.
And they specifically use the Generation 9 overused format, which is kind of like the standard format that people play in.
Okay.
And they tested PokéChamp against a bunch of other bots. So they tested it against Pokemon, which we've already mentioned, and they tested it against this rule-based Abyssal bot and some other simpler bots, like one that just always picks its strongest move, and even a bot that just chooses randomly.
Okay, so a wide range of opponents.
Yeah, and they also did this with 2 different LLMs. They used GPT-4, which is this really big, powerful one, and they also used Llama 3.1.8b, which is an open source model.
Okay, and how did it do it?
So table 2 in the paper shows the results. And when PokéChamp is using GPT-4, it got a really impressive win rate. It won 84% of its matches against Abyssal.
Wow.
And based on those matches, it got a projected ELO rating of 1268.
Okay, so that puts it firmly in the expert level.
Yeah.
And that's using GPT-4. But what's really interesting is that when they used Llama 3.1.8b, which is the smaller open source model, it actually outperformed Pokemon, which was using GPT-4.
Really?
Really?
Yeah.
So it's not just about the size of the model.
Yeah.
It's about how you use it.
Exactly. It suggests that the architecture of PokéChamp and the way that it's integrating the LLM is really effective.
And they've got this nice figure in the paper, figure 7, where they actually show all the pairwise win rates between all the different AIs they tested.
Yeah.
And you can really see how the different bots stack up against each other.
Yeah.
Okay, so it's doing really well against these other bots. They also did some mirror matchup experiments, right?
Yeah, so in these experiments, they gave both PokéChamp and Abyssal the exact same team of Pokemon, and they turned off terrestrialization.
Okay, so they're really trying to control for the effect of team composition.
Exactly. They just want to see, given the exact same tools, who plays better.
Okay, so it's really a test of pure skill at that point.
Yeah.
And how did PokéChamp do in those mirror matchups?
So table 3 shows those results, and PokéChamp did even better in the mirror matchups. When it was using GPT-4, it won 90% of the time against Abyssal.
Wow.
So this suggests that PokéChamp is really good at leveraging its strategic advantages when it has the same resources as its opponent.
Okay, so it can outplay even really strong rule-based AIs.
Yeah.
But of course, the ultimate test is, how does it do against humans?
Yeah, so they put it on the Pokemon Showdown ladder, which is where people play competitive Pokemon online. And they had it play in the Generation 9 overused format for a whole week.
So it's really out there in the wild playing against real humans.
Yeah, exactly.
And they mentioned the time constraints of the online ladder.
Right.
Yeah, so on the online ladder, players only have a limited amount of time to make their moves.
Right. So it's not just about playing well, it's about playing well quickly.
Yeah.
So how did PokéChamp handle that pressure?
Well, they found that about a third of the games that PokéChamp lost, it lost because it ran out of time.
Really?
Yeah.
So even though it might have been making good decisions, it just couldn't make them fast enough.
Yeah. Exactly. So its decision-making process, it works well, but it can be computationally intensive.
Right.
But in the other two-thirds of the games where it didn't time out, it had a really impressive win rate of 76%.
Wow, 76% against humans. That's really good.
Yeah.
And they mentioned that it even reached an ELO of over 1,300 after just 50 games.
Yeah.
So it was climbing the ladder pretty quickly.
Yeah.
And that's already within the expert level, right?
Yeah.
And they projected that if you take out the losses where it timed out, it would have an ELO between 1,300 and 1,500.
Yeah.
Which puts it in the top 10 to 30% of players.
Right.
That's incredible.
Yeah. And this is all without specific training. It's really remarkable.
Yeah. But it wasn't perfect, right?
Yeah.
They did notice some weaknesses when playing against humans.
Yeah. So they found that it had some trouble dealing with certain strategies, specifically stall tactics and excessive switching.
Okay. And what are stall tactics exactly?
So stall tactics are when the opponent uses Pokemon that are really defensive and they use moves that heal themselves, and they basically just try to drag the game out and slowly whittle down their opponent's team.
Right, so they're playing the long game.
Yeah.
Okay, and what about excessive switching? What do they mean by that?
So excessive switching is when a human player just keeps switching their Pokemon in and out a lot.
Okay.
And they do that to try and disrupt PokéChamp's predictions and maybe get favorable type matchups.
Okay, so they're trying to exploit the fact that PokéChamp is trying to predict their moves, right?
Yeah, exactly.
So they're trying to be unpredictable.
Yeah.
Okay. And why do you think PokéChamp struggled with these strategies?
Well, the researchers think that it might be because the Minimax search that PokéChamp uses is limited in how far it looks ahead.
Yeah.
So it might not be planning far enough ahead to really deal with these long-term strategies effectively.
You can't see those strategies coming.
Yeah. And also, they found that some human players who knew they were playing against an AI could exploit PokéChamp's tendency to switch its own Pokemon in certain situations.
Okay, so they're kind of figuring out how to play against PokéChamp specifically.
Yeah.
Okay. And they tried.